Calculus 2, Section 6.6, Moments and Center of Mass. What the heck is the center of mass, anyway? Well, the center of mass is a single point where a group of masses can be concentrated. Sometimes the balancing point. And it's important to locate that point. If we're in 1 or 2 dimensions, we can do that in this particular section. When you get to 3 dimensions, or even larger, you need multivariate calculus, multiples, integrals, and so we won't do more than 1 or 2 dimensions. So in this one, we're going to take care of, in many cases, this masses upon a line. So if you have this line, and it's really a line segment, it's a certain length, and there is on this some of these weights, I guess, sitting on here. This has a mass. We'll say mass 1, mass 2, mass 3. Because of gravity, and we'll say gravity is pulling down, each of these has the gravity affecting it, and mass times gravity is a force. So each of these is pushing down, so to speak, on all of this stuff. Now we need to put here a fulcrum, and if we have that fulcrum, that sort of, this is like a teeter-totter, if we call that fulcrum 0, and if this teeter-totter just sits there and doesn't move, then we have found that balancing point at 0. These are then a distance away. This distance is x sub 2 for that m sub 2. This distance is x sub 1. And of course this distance is x sub 3. And when you take and multiply these forces times the distance, you get what is called a moment. Focus times some distance. This one at m sub 1g is down. You multiply by that x sub 1, and this moment is a negative moment, trying to move this clockwise. I'm sorry, counterclockwise. These two moments are positive because they're trying to move them clockwise. And so you have positive moments and negative moments. And if those, all of these moments, x sub 1 times m sub 1 times g, plus these other two, x sub 2 times m sub 2 times g, and x sub 3 times m sub 3 times g, if those all add up to 0, then your system would be in balance. So we're talking about the sum of each of these torques. The torque is this force trying to turn it. The sum of the torques, or the sum of the moments, the system of torques has several different names, is when you add all those up. X sub 1 times m sub 1 times g plus x sub 2 times m sub 2 times g plus, keep on going, however many you have. X sub n times m sub n times g, where g is just the force of gravity in this case. So the moment, okay, I've got to make sure this is clear. The moment is the force So when you add, or not add, when you multiply by that distance, you get a torque. So the moment is different from the torque. The moment is just that force, m sub 3g, m sub 2g and stuff. The torque is when you multiply by the x. So the moment is just that force, the mass times the gravity, force of gravity. Does that make sense? Perhaps I was confusing with that. So these moments is a sum of all these. We'll use k, I guess. K going from 1 to n of the m sub k I think I just messed that up. Oh gosh. M sub k times x sub k. So let me go back. I'm sorry. The moment is this mass times the distance. The torque is includes that force of gravity. So the moment is the mass times the distance. The torque is the moment, which is the mass times the distance, times that force of gravity, whatever that might be. So this is where you have, these are the torques when you include all of this. You can, because g is always the same, factor out that g, and you get the x sub 1, m sub 1, and the x sub 2, m sub 2, until you get up to the x sub n, m sub n. And all of this is the moment. And when you multiply by g, you get the torque. Now, hopefully that's clear. And if the sum of all the torques is 0, then you get a balanced system. Of course, because g, that force, is always the same for all of these, we can factor that out of time. So if the moment is 0, you might have a balanced system. That's if you have this constant force. Sometimes the force is not constant, so you've got to be a little careful. So, also, there's another way to talk about torque. So where do we place this fulcrum? And let me go to a new screen then. For the system to balance. Well, that's that center of mass. There are 2 S's. Okay. So if we take this torque, and if we take all these spots along this line, if we have placed this fulcrum at that spot where you take all these torques and you get 0 and things not moving, there is a point right in the middle this doesn't always have to be 0. This would be where this would balance. And that's what you would really sort of call your middle. Let's not put the arrow there. This is where you have your x bar, which is where this thing balances. So instead of finding if 0 is really here. Let's call this x of 1. Call 0 here. But this is x bar, and this is a distance. Then to find the torque, you have to know where x bar is and find the distance from x bar for this to be a balanced system. So this is the, take the x sub 1 and subtract the x bar, and you've got that distance. Take the x2 and subtract the x bar. x2 is just this part right here. X sub 2. X sub 2 and subtract the x bar. Well, in this case, x bar is 0, so that's really adding, right? But all of these distances then from the fulcrum that balances the system is that x sub m or k minus x bar. This is the x sub 3 minus x bar, if that makes sense. Hopefully it does. So we can use all of these together and say that instead of adding those up, you can use x sub k minus x bar times m sub k times that gravity g. Sum those up. And that's the torque of the system. But this formula then gives us a way to get at this x bar, the center mass. So from that last page, if the system is balanced, if the torque is 0, then this summation, k going from 1 to n, will be 0. Let's do a little bit of algebra. If we distribute that m sub k times g, then we get summation of m sub k times g times x sub k minus m sub k times g times x bar. We're just distributing this. But the summation of a difference is the difference in summations. So summation of m sub k g x sub k minus the summation of m sub k g x bar. Now if we then put, add this summation, this negative summation to both sides, summation of m sub k g x sub k is equal to the summation m sub k g x bar. But hold it, x bar is a constant, so we can pull that out. These, I guess g is a constant too, but we don't need to, I guess let's pull out the g's also. And we have, in this case, both these are not constants, the m sub k x sub k. And now we can pull out the g and the x bar because both of those are constants. And this is m sub k. Divide both sides by the summation m sub k. And the g. So these g's cancel. The summations cancel. Oh, nothing cancels here. So we get this summation m sub k x sub k over the summation m sub k is equal to x bar. You can't cancel this summation m sub k stuff because summations are sums, it's addition. And you can't split this up. You only can cancel if you can do this multiplication out here, not within a summation. And if you need something to explain that, make sure you get back to me. So this is how you find the center of mass. You take the summation of m sub k x sub k divided by the summation of m sub k, the center of mass. This is also the system moment, because it's m times x over the system mass. But now, what about masses distributed over a plane region? Let's see here. Then that last part we talked about on a line, really. So we just used x rather. Now we're talking about in a plane, so we need x and y. And we have all these points. There's call this x sub 1, y sub 1. Say there's one over here. This is x sub 2. Y sub 2. Let's say there's a collection, a finite collection. Say, put one here also. X sub 3, Y sub 3. And for each of these, there is, if you think about a horizontal line, there is a moment about the X and a moment about the Y. So, all of these have masses. Here's has mass m sub 1, mass m sub 2, mass m sub 3. And so where is the center of mass? Well, we're going to call that x bar and y bar. And we'd like to know how to locate that. X bar is the center of mass for the x-coordinate. And you've got to take all these x's into consideration. And once again, each of these can be thought of as a line. You can work those out the same way. So you get the same formula. X bar is the summation of m sub k x sub k over the summation of all those masses, m sub k. And y bar will be done similarly, but now we're taking the vertical component in the sense of this. That's the summation of all the masses, m sub k, y sub k, over the summation of the masses again, m sub k. So that denominator doesn't change. The only thing that really changes is the x and y coordinate. Many times they're going to call this the moment over the moment, capital M's. Now, this is where it gets, to me, I guess a little confusing. This is the moment about the y, and this is the moment about the x. So you're probably wondering why the x bar uses this summation m sub x m sub k x sub k. That seems to make sense, but then this is the moment about the y. How can that be? We've got to think of this as, I think I can do this. Think of this as a laying down, I guess. Instead of being vertical and horizontal, this is laying down on a table or something, where you've got the x and y axis So this is laying down on this table, right? Now there is a point, the x bar, y bar, and through that is the line for the, I guess this new axis for the x bar, y bar axis. This is the fulcrum point that you're balancing on this table. So I sort of think of it as a sort of a thin, so thin that it has no weight and it's balanced there. And if you start placing weights on here, say there's a weight here, well, let's put a little box, I guess. Now this box is really pushing down towards this table. And therefore, since this is the line y equals y bar, and this is the line x equals x bar, then as you're pushing down, you are doing this moment because you're measuring from and this distance is the y coordinate minus y bar. If I can put that in here somehow. Y minus y bar. We'll call it y sub 1. This is our mass sub 1. This y minus the y bar stuff is pushing down here, and it's trying to move it about the x. So you use this y sub k stuff, you're using the y minus y bar idea, which means it's got the moment about the x-axis, and the x, which is this value, minus the x bar gives you this distance. Then remember this is a negative, so that's why that works. That's the x minus x bar. The x, because that's the x bar. X minus x bar, that gives you the moment around the y. Does that make sense? And they're going to use this, so you gotta have that sort of straight. When you're talking about x bar, you're still using the x values, but it's the moment about the y. Y bar is still y values to calculate the moment about the x. If that makes sense, I hope so. This is the way I think about it. But things switch only when you talk about moments. Maybe that's the way to remember. I don't know. So let's move on to a thin, flat plate. And what do we want to do? Of course, find the center of mass. So if you take a picture, say this is a thin, flat plate. It's in a plane. And if you take a representative strip of that, then perhaps you're guessing that we're going to take and add all those strips up to find something. And that's true. This strip we're going to look at has a moment about the y-axis and a moment about the x-axis. So if we, I don't know if we need to put those in, the y-axis and the x-axis. You can think of the mass of this strip being centered at a point. Now we've already used x bar and y bar, so we can't use that. So this center of mass for the strip is going to be x tilde y tilde. Tilde, T-I-L-D-I. I'm not sure how you spell it. T-I-L-D-Y? Anyway, tilde. The little squiggly line instead of the straight line. It's not x bar, y bar, x tilde, y tilde. That's for each strip. And for that strip, this strip, we've shown it here sort of taken vertically, and that's because we're sort of used to using dx, and that's why we're doing that. You can take it horizontally, and then you would use dy. But the moment of the strip about the y-axis is x tilde times delta m. Let's see. Moment about y-axis, remember, this is where it switches, is the x tilde delta m. Now this is the mass. This need not be the same mass all the way through. This mass can be found many ways. We're going to look at that in a second, though. This is just the mass, which we can assume is always at that center point, the entire mass. But this doesn't have to be a constant or anything like that. It can change as you move up and down the strip. Okay, so the moment about the x, that's just the moment about the y-axis for the strip, right? The strip. And the moment about the x-axis, the moment about the strip is y tilde delta m. And now remember, that's this switching stuff. So with this idea in mind, you can say that x bar is the m sub y, the moment about the y, over the total mass, which is the summations of, remember the moment about the y is when you use x tilde delta m over the summation delta m. The moment, center of mass for the y coordinate is the moment about the x over the total mass, or summation, remember x uses y, and also it matches the y bar, over the summation of delta m. Now, we can take these and make these strips very thin and take the limit as n goes to infinity and do all that same stuff for the Riemann sums and really change this into integrals. So the way we're going to use it because of those Riemann sums, the x bar will be the integral of x tilde dm over the integral of dm. Now this dm is the mass stuff, so it's not dx yet. It's not dy yet. And y bar is the integral y tilde dm over the integral of dm. Same as this dm over here. So that's how we're going to use stuff to find the center of mass. At x bar, y bar. Okay. Just a second and we'll go to a new page. Okay, so I just recopied what we had at the last page, at least the bottom. So let me make sure. this is still clear. So you tell me, in a sense, which of these things up here is the moment about the x-axis? Which one is the moment about the y-axis? Which one is the mass of the strip? Well, the moment about the x-axis, remember, is when you use the y. So this numerator right here. The moment about the y-axis, then probably you got it, it's when we use the x. The mass of the strip are these two things here. So, when they ask you questions and say, find the moment about the x-axis, you don't have to find x bar, you find the integral of x tilde dm. Did I say that right? About the x-axis is y tilde dm. The y-axis is x tilde dm. The mass of the strip is just the integral of dm. And what are the steps for doing this? Well, I think we need to, if you can, draw a plate. Draw the region in the plane with a strip parallel to either x or y axis. And that may depend upon what you're given to help find this tilde y and tilde x. Which way that you're going to come up with a dx dy. So you're thinking, do I use dx dy? I think that can help tell you which way to go. And then you have to express the x tilde and the y tilde in terms of x and y. X or, I guess, y. Not both, because you want to choose a variable also. And, of course, finally, integrate. These individually, the x tilde dm, the y tilde dm, and just the dm. It's an m. Gosh. Essentially finding the parts of these equations. And, of course, the best way to do this is through an example. So, this is section 6x. Page 356. Number 4, find the center of mass. Of the region. This is bounded by y equals x squared minus 3 and y equals a negative 2x squared. Okay, so first we want to graph it if we can, and since I know what this looks like, you can put it on your grapher if you'd like, but this one's not too bad. This is a parabola that opens up. This is one that opens down. The vertex for this one is down 3 units. It crosses the x-axis when y is 0 at plus or minus the square root of 3. So the square root of 3 is like 1.7. If this is 1 and negative 1. So it does something like this. My gosh, that's horrible. Anyway, this one, the vertex is at the origin, and it's a little skinnier. So when you plug in a negative 1, you get a negative 2. When you plug in a positive 1, you get a negative 2. So it's here that it's trying to go through. And if you plug in a 1 or a negative 1, you get the negative 2. Did I say positive? Both of these are negative 2s. So it's essentially like this. And this pad is so smooth and slickery that don't always draw these nice and smooth. Need a representative strip. I'm going to make it vertical because I want to use dx. We need the center of mass of that strip. This is the x tilde y tilde. But we need to represent that in terms of x or y. I want to do it in terms of x in this case. So the x tilde if I want to know, I guess, the center of mass for this, if we assume everything's concentrated at that point, we can use the midpoint of this. If we take this length, you need this y value, but it's negative, so you're going to need to take the opposite of that. So if this is x, this unit here is x, maybe that's a good place to start. Because if that's just x, that's what the x tilde is, just x units away from the origin. The y tilde is the one that's going to be a little crazy, because I'm going to take the midpoint of this line, so at x, which is, if you take this negative 2x squared, and if you want the midpoint, then you add the two together, find the average, and it gives you the center. So you're going to take the negative 2x squared, you're going to add the x squared minus 3 and divide that by 2 to find the center. Which, when you multiply things out, or you don't have to multiply, just add things up and divide by 2, get a negative x squared minus 3 over 2. Okay. So here's your x tilde. Here's your y tilde. So we've got those in terms of x. We need dm. Well, what we'll find is all the time it's going to be some constant, we'll call it delta, of the mass. It could be a function, but if we're not told that function, then we can't do anything. We just say it's some constant times the area, and we're going to call that dA, because we want the area of this little strip, which is the dm. So we want this little area. Well, the area of the strip, first of all, delta, we don't know what that is. It's some number. If they give us the number, we can use that. If they give us a function, we can use that function. It'll be delta of x. But the area we can figure out, this strip is just the length times width. Now, the width is dx. The length, we can't use that midpoint. We've got to take this length. We've got to take this length to the x squared minus 3 and subtract this negative 2x squared. But we also want things positive, I guess. So the length is really, if you take the opposite of the x squared minus 3, and you subtract the negative 2x squared, which may seem crazy, but you can see what I'm doing, taking that length, this point minus this point, but this is negative, so we got to take the opposite. Okay, delta times, if you combine all that stuff, negative 3x squared plus 3. Okay, that is your dm. So I need that. With all that being said, what is x bar? That is the integral of x tilde dm over the integral of dm, which is, what are the limits? Well, we're going to go from this point, which should match here. This should have been down here, to this point. So x is going from a negative 1 to 1. So all of these have the limits, negative 1 to 1. The x tilde is just x. The dm is the delta, negative 3x squared plus 3 dx. Oops, I forgot the dx here, didn't I? All these need a dx. It's an x. Over, well, this is going to be the same, the integral of delta negative 3x squared plus 3 dx. Now I can go through all those steps, but it really is just doing some algebra until you get this down to a polynomial, and take the antiderivative of all the polynomials. You get a negative x to the fourth over 3 plus 3x squared over 2 over negative x cubed over 3 plus x. This is evaluated from a negative 1 to 1. Running out of room again. But you get, after all the algebra, zero. It's a lot of work to find out it's 0. But does that make sense? Okay, let's look at this. Yeah, oh my gosh, I probably could have figured that out by just saying this area, this region that's enclosed by these two functions is really symmetric with respect to the y-axis. So the x value for the center of mass is just 0. Oh my gosh, all that work. Well, the y is not the same. So we want the integral of y tilde dm over the integral of dm. Now let's at least write it once here. Y tilde is all of this stuff. Oh my gosh. So we got the integral from a negative 1 to 1 of the y tilde, which is a negative 2x squared, I'm sorry, we'll use this, negative x squared minus 3 over 2. That is times the dm, which is the negative 3x squared plus 3 dx over what we found here, which I think eventually was 4/3. Because we already found that before. If you work all this out, once again you get a polynomial I guess we'll write it to 1 last time here. It is 1/6 3x to the 5th over 5 plus 6x cubed over 3 minus 9x evaluated from a negative 1 to 1. My gosh. This becomes let's see, I got, let me sort through some of my scrigglings here. So let me first erase this equal sign because I need a little more room. So we're going to go back over here. We know the denominator is 4/3. The numerator is a negative 32 over 15. And when you multiply or divide by 4/3, you multiply by 3/4. And as you cancel things, 3 goes into 15, well, 5 times. And 4 goes into 32, 8 times. So you get a negative 8/5. So the center of mass, way back, I didn't leave room for it. The center of mass is 0, negative 8/5. Center of mass. And of course I couldn't fit all that stuff here, and it did take some little bit of finagling. Try to not do what I did and try to go so fast that you make simple mistakes. We're going to do another example because this might take a few tries. Now we need to mention centroids, but let's go back to that last example. There was one point in that calculation where we had, this was for x bar, we had the integral, we had 3 delta, we pulled that out. The integral from a negative 1 to 1 of, let's see here, the negative x cubed plus 3x dx. That was the numerator. The denominator was 3 delta integral from a negative 1 to 1 of negative x squared plus 1 dx. And what we found was it didn't matter what they gave us for delta because it didn't play a part, because it was a constant, didn't play a part in finding either x bar or y bar. It was canceled both ways. Those things will happen, and if they do, it's like in geometry when they talked about the centroid. If the density function is a constant, it will cancel, and you can call that center of mass of this region of constant density. Or I guess with constant density. So if they ask you to find the centroid, then they probably are telling you that this is a constant density, and don't worry about the deltas. You don't need to carry those around. It's going to disappear anyway. You can let d equal 1. It doesn't really matter if you're supposed to find the centroid. So, with that in mind, and maybe I need to start a new page, because I'm going to do, and you can look this up, number 24 on page 356. So let's go to a new page. We want to find, or given constant density, find the moment. So we don't have to find the whole thing, I guess. The moment about the x-axis. Of a wire with constant density. And it's on this curve, y equals x cubed from 0 to 1. Okay. So, the moment about the x-axis. That's the m sub x. But remember, this really uses y's. It's the integral of y tilde dm. So, this is where you can get tricked up because of that. So we need this picture. Everybody knows what x cubed looks like. From 0 to 1, it does some curving thing here. So that's that wire. This is the point 1, 1. This, of course, is 0, 0. So now when you're doing this, you need to be able to describe we're going to, let's see, one way you can think of this, it's not really a strip, although you can think of it as a vertical strip, so that you can say, I want to do this with respect to x. But it's not really a strip. There is no area, and therefore, all you'd really need is the length of this thing. It's not an area, it's a length. So how do you find the length of this? Well, if you think of that as a right triangle, this is the dx, and this would be the dy then. And therefore, you can find this distance the same way you do anything, the square root of dx squared plus dy squared. Does that make sense? So that's what the distance is. Because it's got a constant density, you're just going to use delta. So we need, first of all, y tilde. But we know, and this is a little tricky also, I guess. If we're going to do this with respect to x, then we got to stick with all this stuff. Respect to x, that means that we need to know what dy is. Well, we know what y is. It is x cubed. What is dy dx? It's 3x squared. What is dy? 3x squared dx. So we're going to use that here. Okay, and this tilde looks like a cap. Tilde y is really where this is for that x. X is x and y is just y, right? So this is so easy, it's hard, I think. So y tilde is just y, which is the x cubed. So let's see. So I need, this is what I'm looking for. I need the y tilde, which is this. I need the dm, which is the constant delta times this length. But I want this in terms of x, so I need to change the dy to this and square it. So all of a sudden this simple problem seems simple, becomes a little more complicated. This also goes from 0 to 1. That's what the x's go to. It's also the y's, I guess, so it doesn't really matter. But in this case, just to make sure. So tilde is x cubed. The dm is this square root so what is dx squared? How do we find some of these? We can't have that underneath. And in fact, we don't have any dx with this dm stuff, but we really do. So this delta is outside. We have, if I can fit all this stuff in here, maybe I'll erase a little bit of this to get some room. We've got the dx squared, but then we also have 3x squared dx squared. So this delta outside, factor out a dx squared. Okay, we'll write it down here. If you factor out a dx squared, this becomes a 1. Factor out a dx squared to here, this is 3x squared squared, or 9x to the 4th. And you have a dx squared, but you can pull that out and just call it dx. So that's how we're going to do this. So we've got the delta. I'm going to pull that out front. We've got the square root of 1 plus 9x to the 4th, and then the dx outside. Does that make sense? So this is really interesting to me because it sounds like a simple problem, the integral of y tilde dm, but you've got to look at all these parts and write them in terms of x, which takes a little bit of algebra, which eventually, when you do all this stuff, do they tell us what delta is supposed to be? No, they don't tell you what delta is, so we're going to have that on our answer. But in order to solve this integral, I'll give you what our substitution is. Let u equal 1 plus 9x to the 4th. Then du is 4 times 9, or 36, x to the 3rd dx. We've got an x to the 3rd, but we don't have a 36, so I'm going to use 1/36 du to replace x cubed and dx. So the x cubed and the dx become 1/36 du. You've got to set your limits of integration differently and keep that du around, and eventually you get delta over 54 times this 10 times the square root of 10 minus 1. I'll admit I'm trying to match the back of the book, I guess the answer I had for this. So you might get something different, but it may be exactly the same if you distribute this delta. If you rewrite this differently with fractional exponents and stuff, you might get something different. But the key to this problem is, I guess, the answer I like to get to make sure I did things right. But it's how you set it up that's so interesting. Okay, we're going to do another example on the next page. Okay, let's do number 16 on that same page, 356. You've got this region between y equals 2 over x and the x-axis from 1 to 4, which looks sort of like, let's see, from 1 to 4, we do need that fourth quadrant though. So if this is 4, this would be 2, 1, 2, 3, 4. Plug in a 4, we get 1/2 for the y here. I'm sorry, from 1 to 4. Plug in a 1, we get a 2. And plug in a 4, we get a 1/2, and we know it curves. So we've got the same curve here, and if we rotate it around the x-axis, we have a solid that we can use a slice of. So we use the disk method to find the volume. Remember, the volume is the integral, in this case from 1 to 4, because we're going to do this with respect to x. This is the radius, that's the height there, that's the y, 2 over x. It's pi 2 over x squared dx. Pi r squared times the width, thickness. So this is from 1 to 4. Let's pull out a pi and a 4. This is really x to the negative 2 dx. And now you can just go backwards and figure this out. It's not too bad. I'd like to save some room, I guess. So this is the 3 pi is what you get eventually. You should be able to work that one out, right? Add 1, divide by the new power, go from 1 to 4. So you're going to have to do some subtracting because the 1 no longer gives you a nice 0 for that second part of that. That's part A. Part B. And I guess I've changed colors here to try to get back to that same. It's sort of close. Part B. If we are given that the delta, the density, is now a function of x, and it is the square root of x, find the center of mass. X bar, y bar. Okay. So now we're looking at this region we're not rotating it as far as see. This is covering, oh, this plate covers a solid, so I guess it is sort of rotated around. So we got this big plate that we're going to lay out flat and find the point that's the center of mass. Okay. Does that really, I'm going to have to look at that closer, but as far as how to find that, let's change our colors back, make it a little greener. So what is y tilde? Let's do x tilde first. X tilde is just x. We're just going to go for x going from 1 to 4. Y tilde now, and that's why I think this is, maybe my picture is not very good, because y tilde should be halfway up here. So this is 2 over x, and we take halfway up that length. So 2 over x, if we need half of that, we need 1/2 of 2 over x. Which is just 1 over x, or x to the negative 1. The dm, the mass, is the length, which is 2 over x, times the density in terms of x dx times the width. Okay, so now we get 2 over x times x to the 1/2 dx, or 2x to the negative 1/2. So we need this part, and this part, and this part, because x bar is the integral of x tilde dm over dm. So I'm going to write it here from 1 to 4. X tilde is x. Dm is, with the dx here, 2x to the negative 1/2 dx. Y tilde, integral from 1 to 4, y bar is y tilde, which is x to the negative 1, times the 2x to the negative 1/2 dx. Now this is really not completely y bar and x bar, because we need the integral dm. That's the integral from 1 to 4 of this stuff. 2x to the negative 1/2 dx. Now once again, this is just going to be polynomials with maybe some negative exponents. And I'm hoping you can do all that, no problem. This numerator is going to be just 2. Oh, it's going to be 28/3 over the 4, which gives us eventually 7/3. And this is going to be 2, because, this is 4, over 4, or 1/2. So both of these, if you work this out, that's 4. And this is your center of mass. It's 1/2. Did I get that backwards? Yes, of course I did. So it's the x bar, which is 7/3, and 1/2. So does that make sense? X is 7/3, so it's 2 1/3. And 1/2. Interesting. So that matches the book. And so I think what we were looking for as the center of mass was that, just that top piece there. Because we were using the same thing they were using. This is just x for x tilde, and halfway up, that 2 over x for the x tilde and y tilde. We were also using, for the length here, just 2 over x. And then the density function being the square root is x to the 1/2. So, we were doing it the same way as the book. They didn't really ask the questions clearly as I thought. But they did only want it 2-dimensional. So I guess I wondered a little bit, when you get into multivariate calculus, you'll be able to find if this is a cone type of shape, then we would want to find out where that center of mass is, which wouldn't be on the actual cone, because if it were hollow, it'd be inside here someplace, probably right here in the middle, where that center of mass would be for this hollowed out stuff. I don't know. Maybe I'm wrong. But 7/3 sort of surprised me. Oh, because this starts at 1. That makes sense. Okay, 7/3 now, because this goes from 1 to 4. So this is 1 and 4. Half is 2. No, half is 3. 1, 2, 3. So At 2 1/3, we're really back here someplace, which uses this wider area. So that's where our center of mass would be. Okay, it all makes sense, and it should. So if it doesn't, you should look things over, or let me see if I can look at it, and we'll make another video. I like to use all the colors, too. Gosh, this is pretty. Okay, that's the end of the 6.6 section. If you have questions, I'd love to do some more of these problems, so send me a text, and I'll send you a video.